Well, today I'd like to talk about tidal marshes. And I think the best way to begin is to talk about marsh genesis, that is how marshes are formed. Then descriptions of a marsh and marsh modeling the rate of marsh rise, and then marsh restoration projects. So today it'll be all marshes. Marsh begins as a mudflat, just a shallow edge of the bay where the sediment and is typically drained by the lower tides when the tides fall down. And if you look around the shore in a mudflat area, see this is a mudflat area and this is all shore here. What you see is that the slope is toward the body of water, and that there are little rivulets that form that are directly down the slope, just straight drainages that are directly down the slope and enter the surface of the water out here at low tide. Sea level, as I'll show you presently, doesn't just rise, it goes up and down. And average sea level goes up and down, and you can imagine that there are times that it's lower than, some years it's lower than others. Furthermore, the supply of sediment isn't constant, and there are times when a lot of sediment is deposited on these mudflat areas more than normal. In any case, there occurs at some time a year wherein the mudflats are exposed more than normal, and a salt-tolerant grass, the one we saw on our trip to Spartina, can begin to populate this area. Once any kind of vegetation populates the area, then the sedimentation rate goes up immediately. And the reason being that the stems provide velocity gradients that promote aggregation. They also shelter it from erosion by wave action and from wind. And so the material that deposits there stays there. And this area will begin to accrete rapidly. That is, the elevation of the surface will rise. Suppose I take a section through here. And what you'll see is originally there'll be a mud flat with a slope, I've exaggerated the slope, and then the shore going on up something like this, and the water going out here. As soon as plants appear, then the sedimentation rate increases with the result that the surface elevation rises. And of course, once it rises, it's still more favorable to plants, and the plants become further established. And so it continually rises. Eventually, it will rise to the point, eventually it'll rise to the point where it actually begins to invade the land. The land has a gradual slope. So the evolution of a marsh is up, it grows upward. The drainage pattern at first will just look like straight drains, so the original drains that were there, and this will drain. There may be some little rivulets on alongside, but it will generally drain back to the bay and drain the area pretty thoroughly. Once it's gotten up to the point where the surface is fairly level, however, then each flood causes water to flow out the sides of the channels when it comes up, and the tide gets as high as the surface. And the material that flows out of the channels drops its sediment. It has the highest concentration that comes out of the channel, and the particles that settle fastest settle right by the side of the channel. So you get, I'll call them natural levees, just like you have in streams, alongside of each channel. Actually, they're fractions of a foot high, but it's just a little bit higher. And as a result, the area between these channels is lower than the area right next to the channels. And these little channels will erode headward back into those shallower areas. And you'll see, I should have brought some examples. You see, what you see is that first you have these straight channels, then you see these little crooks at the end, and some of these may go back into other areas. And of course, once they have eroded back into the lower areas, then those areas tend to fill. the consequence is that it develops a dendritic pattern. Well, of course, then as the marsh continues to rise, sea level's rising, and the marsh continues to rise, then the drainage erodes headward into the area that newly occupies the land. And the result is that as it invades the land, these develop dendritic patterns, serpentine kinds of patterns. I'll show you some in a minute. And the result is that the whole area is irrigated about uniformly, irrigated and drained uniformly. The water rises, runs over the sides of the channels, floods the area, and then it drops. The consequence of that is that the tidal marshes are flat. The whole marsh may vary, the highest and lowest points, except for the channels, of course. The highest and lowest points on the marsh plain may be 3/10 of a foot apart. You know, it's really flat. Another thing that happens is that the wave action tends to erode this original face, so that the marsh grows upward, grows into the land, and the face tends to retreat slowly. We saw on the field trip, we saw some bank erosion resulting from wave attacks on the face, and that's typical. You see a little cliff there, a little drop off at the end. So one of the things I'd like to keep in mind are, first of all, a marsh grows by sedimentation upward. It invades the land if the land slope is flat enough, or it's flat, and it's very dependent on vegetation. That is, the vegetation is what changes the process from just a mud flat, which is eroded by waves, to a marsh that grows upward. Now, as the marsh grows upward, it's think of plot here of time and water surface elevation tide here. Tide made something like that, for example, and as the marsh elevations may start at that elevation, it's flooded during the time that the tide exceeds, the surface of the water exceeds the elevation of the marsh surface. But you can see that as the marsh accumulates sediment, then and rises to a higher elevation, then the duration of flooding and, in fact, the frequency of flooding both diminish. Follow me? So that as the marsh surface elevation rises, its opportunity to collect sediment becomes less. And in fact, it would asymptotically approach some level and stay there if sea level didn't move. The rate that the marsh rises depends on the suspended solids concentration of the water that floods it and the water that floods it. So if we had now one other fact I should point out, and that is that sea level is rising at an appreciable rate on the scale, time scale of marsh elevation. So that when as the marsh elevation gets high and it gets flooded less and less by the tide, less frequently and for shorter periods by the tide, then its rate of rise would gradually diminish. But if sea level is rising at the same time, then sea level would tend to flood it, as sea level rises would tend to flood it more frequently and for longer duration, so that would accelerate its rise. So you can see that if we had a steady rate of rise of sea level, a uniform concentration of suspended solids, that the marsh elevation eventually would assume some elevation relative to the tidal datums. You follow me? In other words, if sea level is rising, then the marsh rises too. If it lags behind, it gets more sediments, which makes it catch up. Well, I've expounded this as though it were gospel. I better tell you where it comes from. Well, it comes from two things. One is cores. Take core samples, and what you find as you go down in the core is plants plants that have been smothered by mud. And you can go down quite some distance. In some places around the bay, in the Mosaic Marsh, for example, about 80 feet. You know, when the marsh has grown up, we're talking about geologic time. Well, not 6,000 years, 7,000 years. Another is the configuration of the channel. What you find if you go out on a marsh is that the channels have walls straight up and down. The marsh grew up around the channels. That's not typical of streams ordinarily, just straight up and down. And in fact, as the marsh grows landward and the area that's flooded and drained increases, then the channels out here have to erode to handle that, or erode as a result of greater amount of water, and they tend to erode underneath the top. So what you often find is slightly overhanging banks out in this region. But up here you find that the banks are, up in this region, the banks are straight up and down. Some of the rivulets are just a little bit wider than your foot, and maybe 4 or 5 feet deep. So when you're walking across the marsh and step into one of those, you realize that they're straight up and down. I learned about marsh channels in about 1942, when on Easter, when I went with a friend and a duck hunter across South San Francisco Bay over to the Leslie Salt area. It was abandoned at the time, and this duck hunter wanted to build a wharf and a house for his duck hunting expedition. So he went over to salvage some timbers. He had a boat about 20 feet long and 8 feet wide, and it drew about this much water, so he could get in shallow water, build a little cabin on it. And the three of us went out, went up these marshes and marsh sloughs, and I got off and explored the marsh, one of the marsh areas there, and then came back to the boat. I had on hip boots, and I stepped up to what looked like ground right next to the boat and reached for the boat, and my feet went out from under me, and I went down way over my head, straight down. It was pitch black down there. And, it was so sudden and so quick, you know, I couldn't imagine a bank being straight up and down. Well, there was a slight overhang, and underneath it was just straight up and down. Well, needless to say, I came back up and got aboard the boat. I learned quickly that marsh channels have certain slopes. Oh, let's see. Oh, and the other thing is that this vertical slope, as the channel gets deeper and deeper, as the marsh grows up more and more around the channel, the slopes eventually become unstable and fail, just regular cylindrical failure, and you can go out in marshes and see those sloughed off sides of channels where those have failed, and they last a long time. They stay there for a long time. Well, I brought some transparencies to describe the marshes, and this is an old map of a marsh made in the days when they mapped with a plane table. That isn't very good. One place you can do it in the backbone. Would you mind? That would be bad for you, though. But how about over here? Can you see that? Everybody see that?
I realized there was no screen.
That better? Well, you can see the channel. First of all, you can see the ragged edge of the shore where the bay is, the waves on the water eating away from it. And you can see the channel is wider near the mouth than it is back up here. It's eroded as the marsh invaded the land on the east side of the marsh there. And you can also see the nature of the channels. They're little channels with smaller branches on them. For example, this channel has another one with a branch here, and there are little branches off a bit. Some of these little squiggly ones are just little narrow grooves, but deep. Typically, they're quite deep. This is the marsh off of South San Francisco Bay. I'll show you where in just a minute. And I think the map is about 1855 or 56. But it shows a typical old marsh. These are little Coyote Hills. Right there. And there's another one down here somewhere, right there. So what I'm going to show you the results of a core taken right by the little Coyote Hills here, and another one taken down in this region.
So the hills were there before the marsh came?
What's that?
The hills were there before the marsh?
Oh yes, the marsh grew up around the hills. When we went across Highway 37 on Saturday, you saw those hills in the distance, and it was flat. Well, all that flat area was once marsh and diked off for agriculture. And it all built in the same way New York fallout. But from this point on, it's fallout in San Francisco Bay area. You can see that there's a sharp peak at about 1963 fallout. This is cesium 137. It's a gamma emitter, and it has a 30-year half-life. Well, it's been 30 years since, just 30 years since that fell out, and so the amount that you find now is pretty small, half as much as it was. We used the elaborate counter out of the dog project, the Beagle project. It's a very elaborate vault and counter system to count slices of the core and find out when 1963 was. Then we used that to adjust the model. I'll show you. Another complication you run into, I just have to show you this, is that you have all these datums to deal with. This is the Presidio staff gauge that I showed you earlier, and these are the numbers on it. And this is the same thing referred to mean lower low water. And this is mean lower low water at the Dunbarton Bridge. Mean lower low water datum values, and then the NGVD values at Dunbarton Bridge. And the reason we needed NGVD is that we determined the concentration by running the model so that the elevation at the end of the total run was the elevation that it now had. That we surveyed the area and determined the elevation and adjusted the concentration until it made that elevation. Then, I forgot something. First thing we did was to assume that the initial condition was one where the marsh was in steady state relation to the early rate of rise of sea level. We assumed a uniform density of core, solid from the core, and we assumed that the concentration was constant. So those are major assumptions. Now, one of our problems was to get a good running start, you need to start well before 1850. We started at 1820, and in order to find conditions in 1820, we want to start back here. We extrapolated this period linearly back to 1820. And then assumed that the marsh was in steady state and calculated the size. We started out assuming that the 1963 level was the level shown up by that plot, and then made small adjustments to improve on it. This is a plot showing the radioactivity microcuries per gram of material, and you can see that it forms a peak, looks something like this. In 1963, these are elevations of the core as predicted by the model in 1970, 1965, and so on. This is for the marsh core that was taken over by the hills. You'd expect very little subsidence to have occurred by the hills. Marsh should be pretty shallow there, and we found that there was about 5.9 centimeters of subsidence over the whole subsidence period from 1917 to 1973, which is not very much subsidence. One of the people from Geological Surveys said that they expected very little subsidence at that location, and that's what we found. 5.9 centimeters is, not so much.
Is that because there wouldn't have been so much clay there? It would have been mostly sand and it's...
No, it's because it's on the hills, next to the hills, and the hills go down like this. Yeah, there wasn't much clay, and the aquifer was probably over here. For the other core, which was in an area that had a greater rate of subsidence, well, first of all, for that same core, let me show you the calculated elevations of the marsh relative to mean high water. Of course, the marsh is rising all the time. The sea level is rising all the time. But so the relevant thing is this elevation relative to mean high water. This line represents mean high water over the period of 1820 on. And of course, at first it's just steady because that's what we set it at. It's unsteady at night. Then the fluctuations are due to the fact that sea level elevation was fluctuating. Then during that period when sea level was actually diminished, remember from about 1880 to 1920, you can see that it rose here. And then it leveled off and fell off a little bit due to subsidence, but otherwise it just rose as sea level rose. The marsh, the other marsh, however, also showed a peak in cesium-137 activity that we adjusted in 1963. And but you can see that in this marsh where subsidence was greater, 56 centimeters, that's almost 2 feet. Now you can see that the marsh accreted very much more rapidly. This spread out much more compared to the previous plot. Between 1950 and 1970, it grew from about, say, 17 centimeters to about 37 centimeters, about 20 centimeters. And the plot of that relative to mean high water clearly shows the effect of subsidence. We started out with it at about level again, and it looks much like the other one did, up to the point 1917 when subsidence started, and then fell off, and remember that subsidence leveled out and fell down again, and that's reflected here. And in fact, it got down almost to mean high water elevation at the end of subsidence, and then it creeps very rapidly when subsidence stopped.
The farmers were pumping as early as 1920.
1917 is when the subsidence started.
So that's when was there any pumping before then? Was it one of the pumps?
There was well, I lived there in the 30s, in the early 30s, and water was flowing over the casing during the 30s. The pumping really started, the removal of groundwater started earlier. I think that's kind of a description. You can see what the processes are that determine the elevation of the marsh and the effects that any changes in those processes will have. Sea level rise increases, affects the relative height of the marsh. Concentration of solids increases the height, or if it decreases, it decreases. So the marsh is really a dynamic system that responds to its environment. And in fact, it responds pretty quickly to its environment. We're now faced with another problem. About 80-some%, some people say 90%, of the marshes around the San Francisco Bay system have been diked off so that the wildlife, waterfowl particularly, no longer have that large marsh area for feeding and resting. And the conservationists are very much concerned about reversing that trend. The diked off marsh lands, like that we saw in Highway 37, are the clay soils that marshes are made up with. And when the land was drained, the soil dried and shrunk, so that it shrinks to about 60% of its original wet volume. So that lowered the surface of the land, just having it shrink. It also oxidized, and the sulfides in it became sulfates, and makes the soil very acid, and it makes it difficult to grow plants. The salts in it, which can be washed out to some extent, but it's not very permeable soil, so it's very difficult to get the salts out. It's only useful for very shallow-rooted crops, shallow-rooted, salt-tolerant, acid-loving crops like oats. And even oats suffers from the acid and salt condition. Nevertheless, it was used for pasture for dairies, for cows mostly. Not pasture, for hay. And the hay, even today, even though it's been raining for 100 years, the stalks are only 18 inches long. You know, it's a pitiful looking crop. But it was used, it's been used all that time for crops. The conservationists are making a pretty effective effort to buy up that land and convert it back into marsh area. Well, I should say also that sea level's risen since 1870, as you saw. It's about 7/10 of a foot a century, so it's more than 7/10 of a foot higher. The combination makes the land about 2.5 feet below mean tide level. Now, in order to convert that back into marshland, it's necessary to raise the level of the sediment to the point where marsh plants can grow. And we no longer have the luxury of the edge of the bay that I described before. Now it's land that's been diked off, and somehow we have to bring the sediment to the level where plants can grow. Also, we need to make that is, raise the level so that the period of inundation is short enough so that plants can become established. The most inundation tolerant plant is Spartina. In fact, all 4 varieties of Spartina seem to be salt inundation tolerant. So you need to get the elevation a bit up. Also need to have substrate, that is the sediment surface, be suitable for plant growth. The Spartina likes fresh mud. It doesn't like old mud that's ever been dried. It likes fresh, soft, open mud. There have been quite a few marsh restoration projects fail, and one of the main reasons that they failed is they put in mud and let it dry or partially desiccate, so that the plant can become established. Then the third thing that's required is that the entire area be drained with every time. That is, that there are no ponds left that can evaporate and salt accumulate. So the drainage, the elevation of the marsh relative to local tide level, this material that's deposited, so the plants become established, is important, quality of it. And thirdly, the drainage has to be complete. The whole area has to be drained. Otherwise, you have salt dams, or at least barren areas that are from salt.
Why don't you have a problem then when we were on the field trip in that one area? Remember when we walked really far out into we had the marsh on one side and then a little pond on the other side?
On the other.
Yeah, there's just a mud flat. Doesn't that have salt accumulation problem?
There is, yeah, that's part of the reason that plants aren't growing in there.
Yeah.
And the fact that it's partly dry.
How much soil do the plants need? Are they shallow rooted plants?
Fairly shallow rooted. And
So they don't need
maybe,
it.
are there botanists here who know about I think Spartina multiplies by corms as well as by seeds. That is, its roots go out and it comes up from roots. Any biologists here? No, that's all I know about it. I know what it takes to make them grow, but that's, like a farmer, I don't really know much about the plant itself. And you learn about what it takes to make them grow by going out.
How much soil do you have to put to
The
begin
soil's
with?
freshly deposited mud.
About what depth do you need for a start?
I allow 6 inches. That's enough.
So much.
That's enough. You can have old decayed mud or old hardened mud under that. But you need at least 6 inches to make them grow. They seem to do very well, just about 6 inches. Well, and of course, you need to, right?
I'll let you can finish now.
You need to make sure there's a supply of mud, sediment in the water that comes out.
Yeah,
Because the marsh, you want to put the marsh into the normal mode of growth. You want it so that you never have to come back and do something to it. But you want to insert it somewhere into the mode of growth that I described here, so that forevermore it will be a marsh. Now, that's another cause of marsh restoration failures. People have tried to make mechanical gates and things to make it. One marsh I worked on, they made a mechanical gate, and they wanted a small tide down low where the marsh was. They didn't want to wait for it to fill up. Well, it was a disaster. It was awful. Anyway, and of course, one of the problems is that there isn't somebody out there all the time to keep the gate working. You get a log in it, and nothing happens until somebody happens by to see it. It doesn't. So, principle I expound is that you want to make a marsh as nearly a natural marsh as you can, and one that will continue from then on without any attention to that.
If you have a marsh and you didn't drain an area properly, can you go in afterwards and drain it and it'll properly
If it isn't
revitalize?
draining properly? Well, if you, depends on the situation you find. If you find a situation that isn't draining, then you have to provide drainage. Out in Mosey Marsh, you saw those little ditches that we put in ditches. We just put in narrow ditches and they eroded wider to little basins that weren't drained, and made sure that they drained. I don't think there are any areas out there that don't drain now. I haven't flown over it lately, but last time I did, I didn't see any spots where multiple sizes were drained.
And if it did, you could just supply drainage and it would solve the problem?
Solves the problem. If you drain it, well, if salt's already accumulated, then pretty hard to get plants started. Now that, we started out before that was flooded, so we could provide drainage before the salt had accumulated. I worked on another marsh up the estuary ways where the salts had accumulated. And I don't think there's any hope unless you're willing to go out and pick it all up, clean it out.
How about using dredge soils for marsh restoration? Do you have any experience with that?
With what?
Using dredge materials?
No, that's one of the things we're studying here. Now, you can see some problems with that.
Yeah, what have you seen so far?
Well, one of the problems is it may not be, usually dredge material is anaerobic, and you may have some difficulty getting it
Getting the plants started?
for the plants. I think probably it'll oxidize quickly enough there. It's never been drained dry. If it's barged and allowed to drain, you might have some problems. If it's pumped in, kept wet, pumped in, then the important thing is to pump it in a way that produces a draining surface. For example, what we're going to propose for Wisdom Marsh for that is, well, two things. The marsh area looks something like that. And that first transparency that I showed you that the dendritic pattern. If you look closely at those, you find that no one drain drains more than about 300 acres. And you can imagine why. If it gets too big, then you don't have any slope to drain it with. So the first thing we did was to break this up into 5 pieces, each of which was about 300 acres with an opening here. And what we'll recommend for filling it with dredge material is it will be pumped in and discharged various points around the perimeter, so that all the drainage will be toward this, that is the drain. If the channel runs base on here. But by it comes in as a slurry, about 5 times the volume it comes in deposit. And by pumping it in around the periphery, then we can expect this material to form a slope toward the center of the drain. And by making it in small segments like this, we can keep it manageable. We haven't gotten that far yet. I'm just talking about.
Interesting. Is that Guando's project? Is Guando the new stretch?
Guando's
Okay,
doing it.
yeah.
He's using RMA2. That's a two-dimensional finite element to calculate the water flow, water distribution in here with a tide change out there with different configurations of inlet channel. And he's using SED-H, another finite element sediment transport model, to model a deposition inlet in the area. And he's doing it by stages. The models the flow on the present. We have a topographic map at the elevation, measuring the flow under present conditions, and then measuring the sediment for a 14-day tidal period, and multiplying that by some factor to make it a year, say. And then the new bed configuration has to be put into RMA2B model to get a new hydraulics and so on, and determining the shape of the bed with time. And it turns out that when you have a channel down here, that it doesn't fill in here quite as fast as it does up here, as you might imagine. He's trying various configurations of channels. I'm going to talk about models next hour. But I think I've expounded the principles. The most important principle is join the natural processes. I guess that's number one. The second one is be sure that, in order to accomplish that, be sure that you have adequate sediment supply. There are lots of good marsh sites, marsh restoration sites without a good sediment supply. That, that can be a serious problem. The third one is provide complete drainage. And the fourth one is provide a suitable substrate at an elevation the plants can become established. I guess the one that most commonly causes problems is the suitable substrate mud. You want fresh mud. That's never allowed to dry, to desiccate. Once it's desiccated, then it's hard for plants to become established. Spartina likes soft mud. One time I was walking out in marsh near Burlingame with Tom Harvey. He formed a firm called Harvey and Stanley, famous for marsh work. Calviso. He and I were walking along one time and we were talking about Spartina. There was a bunch of Spartina isolated from other Spartina, and we were walking alongside it. And he said, gee, that's funny. He says, Spartina doesn't like hard soil. I can't imagine how that is. And I walked over and picked up a piece of driftwood, handed it to him. I said, Harvey, push that into the mud over there. And he went over and he just fell on his face. It was soft about this far under the surface.
You know that one.
I appreciate it. Very kind. One other thing I'd like to say, and this is pushing the edge of my confidence, and that is, I strongly believe in providing the conditions that plants like for a marsh to grow, and then letting the plants take over. You find some agencies strongly recommend planting. They're impatient; they want to get it planted. But in order to plant something in soft mud, you have to get out there and disturb the mud. You have to raise the plants and separate them and all that. I think that's just evidence of patience. I think letting it establish itself provides a much more natural system and one that will continue to grow. I might say a couple of other things about marshes. Not going to refer to the San Francisco Bay system, but marshes in general. I mentioned that the sediment supply is really important. In some areas, sediment supplies are diminished by man's activities, drainage of land and vegetation change. And then the marsh, if sea level rises, the marsh becomes drowned. That is, the surface can't keep up, and pretty soon plants are gone. So marsh is lost. The place on the East Coast, for example, the marshes are just drowned from lack of sediment supply. Another thing that I should mention is that as the land surface, the marsh surface rises, the kind of plant that exists typically changes, goes through a change from Spartina to common lake pickleweed that we saw. But there are at least a dozen other plant species that are very common in high marshes. You find the Spartina, almost pure Spartina, close to the water at lower elevations because it can stand the inundation. But as your elevation gets higher, then you get a mixture of plants that's, in this area anyway, dominated by the Salicornia pickleweed. Occasionally you'll see places in marshes that are high enough for other woody plants to become established. There's a greasewood that we saw out there. Typically will develop on the edge of the marsh and where it's invading the land. Then finally, I should say, with regard to man's impacts, if you have a marsh shore like the one we looked at with dendritic patterns in it, so if the marsh is diked off somewhere back in it for housing development or other development, it's very common in this area, then this channel will fill in because there's no longer all this will flow out from behind it. Kept it scoured out. It will fill in and it will fill in pretty fast, and Spartina will grow and fill in, leaving a small groove in the center. And Spartina will grow on that fillet on the sides, and then it'll rapidly grow, just as we described the marsh growing earlier. And pretty soon you'll have a marsh that can stand out there and you can hardly see any channels at all. The Hirt marsh, just north of the marsh that we went out on, is like that. It had large channels like this. It had been diked off for development, and the marsh channels had filled in and become dominant. You can open those channels again and they'll go back in the natural process. The Audubon Society wanted to have ponds and channels in Hirt Marsh, and we went out there and explained to them that what you have is a natural system resulting from the levee that's blocked off the channel. So beware of restoring a marsh that's already a marsh, but now has different drainage configuration. I think the fundamentals that I've described can maybe cope with any of these situations that you run into. There's going to be more and more marsh restoration projects, and I hope some of you get involved.
Do they have sites in the South Bay where they want to do restoration?
Restoration. There are a lot of small sites. Most of them are just a few acres. The one I mentioned where they had the mechanical device, Charleston Slough in South in Mountain View. It's a quarter of a mile long and 100 yards wide to the outside. It's a very narrow area. The South 3rd Avenue widening project was just not much bigger than this building, I guess. Most of them are pretty small. There aren't many 1,500 acre ones. That's the biggest by far. There's a 300 or 400 acre one over in the bottom on Petaluma Creek. It's going in now. And I designed one for Government Keys. It's probably 50 acres. And I think, and there's one at Collinsville, if that's built, that may be a very large one.
Where is that?
That's up the estuary, but it will be filled with dredge material, and there'll be a lot of upland wildlife habitat, not just marsh. Then the Fish and Wildlife Service has expressed interest in Skaggs Island. Skaggs Island is a naval radio station, antenna farm. And I think only a small part of it's antenna farm, most of it's just farmland like the Coleman Ranch. And that's going to be a difficult problem because it's far from San Pedro Bay, far from any sources. So it's hard to say what's going to happen.
You could do a dredge marsh there,
Dredge
right?
well.
Yeah.
That could handle. We'll have to overcome some
I mean,
ill
after-
feelings with
After going
Fish and
down.
Wildlife people say they don't like dredge spoil. So, but that's probably not. Then, of course, this area was all once marsh, this was all tules and marshland. I suspect that more and more of this will be in small pieces be made into marsh. That's all I had to say about marshes. Any
That's interesting.
any questions? Next time I want to talk about modeling, and I probably ought to have Mike talk about modeling. He's been doing it for the last couple of years, about hydraulic models and sediment models, and not so much about numerical techniques as about the fundamental philosophy of models, and what you have to watch for to make them work successfully. I'd rather not